Helmut also pointed out that the shear behavior of panel zones, though it was somewhat problematic in terms of the deformation patterns it introduced into buildings, that in addition to having significant impact on the way a building would deform, also had some very desirable energy dissipation characteristics, and that therefore, used properly and with the appropriate caution, could be a preferred mechanism for dissipating energy, as a steel frame experienced earthquake shaking. So, Helmut's early work in this occurred in the late 1960s, early 1970s, and I decided to conduct a survey of the codes to see when it was exactly that Krawinkler equation made it into the codes, and that his warnings on the proper use of panel zones were heeded by the profession. So I started by looking at the first version of the Uniform Building Code that I actually practiced with. This was the 1973 Uniform Building Code, and I looked at the requirements for special moment-resisting frames in that code. The first one was that the connection must be capable of developing full plastic beam capacity, unless, of course, you can demonstrate that adequate ductility can be obtained if you don't do that. The second is that if the ultimate tensile strength of the beam material was less than 150% of the yield strength, then you can't allow the beam to hinge where there are weak net sections, meaning bolt holes. The third one was that the members had to be compact. The fourth one is that when you're evaluating the slenderness of columns, you couldn't assume that the columns were braced by other columns in the building. You have to consider that was an unbraced frame. And the fifth one was that you had to do non-destructive testing of butt welds of primary members of the frame. And that was it. A quarter of a page were the entire requirements for special steel moment-resisting frames in the 1973 Uniform Building Code, which is why I guess I was surprised in the early 1980s when I started studying for my structural engineering license, after having designed many steel moment-resisting frames and never having actually designed a panel zone to be strong enough to develop the strength of the beam that was connected to the connection. I was so surprised to read in the Blue Book that this was an issue, because in fact the code didn't require it. And so when I went back and did this survey, I actually went back and did a little bit of research, and I looked at the font of all structural engineering information in California. In fact, one of the books I used when studying for the said SE exam. I looked at what it said about beam column joints and panel zone strengths, and what it said is, since 1969, the Uniform Building Code has required that beam to column connections develop the full plastic capacity of the beam. But this requirement was never specifically extended to the joint panel zone, so at least I wasn't the only idiot out there who was ignoring the panel zone. Well, of course, by the 1976 Building Code, this must have been corrected, right? So I looked at the 1976 Uniform Building Code, when all the major lessons from the 71 San Fernando earthquake were incorporated, and what did I find had changed? Well, they upgraded the plastic compactness requirements for structural sections used in moment frames, but no mention of panel zones. This must have been an oversight. Let's look at the 1982 Uniform Building Code. What's changed there? Well, we've added some new material grades, but that's it. Let's look at the 1985 Uniform Building Code. By the way, the Uniform Building Code was a wonderful code. They used to draw these little lines in the margin when they changed something. So you can see there's no lines hardly in the margin. They changed hardly nothing in this code in all these years. But again, they decided that some of the grades of steel that were added in the previous edition were perhaps added foolishly, and out they came again, and still no mention, some 14 years after Helmut's first research on panel zones, of anything dealing with panel zones. Finally, in 1988, with a complete rewrite of the seismic provisions of the Uniform Building Code, extensive requirements on panel zones make it into the building code. And here is where, for the first time, we see in the building code the so-called Krawinkler equation, which provides a formulation for determining the strength of a panel zone in shear. And true to what several of our speakers have said about Helmut's work over the years, this equation was derived through a combination both of analysis and experimental work. And in fact, you can't actually derive this equation strictly on analysis. It accounts for a significant amount of strain hardening that occurs in the panel zone, as demonstrated in the test. Now, the Krawinkler equation, as impressive as it is not actually the most impressive thing about these provisions that appear in the building code. And so what I would like to call your attention to is the even factor, which tells you how strong the panel zone actually has to be when you're checking its strength by the Krawinkler equation. In the words of the code, they're probably too small for you to read, so I'll read them here. The panel zone of the joint shall be capable of resisting the shear induced by the beam bending moments due to gravity loads. That's good. You probably don't want your panel zone yielding under gravity loads. Plus 1.85, that's the Krawinkler factor, 1.85 times the prescribed seismic forces. Of course, the prescribed seismic forces are 1/8 of the demands that might occur in a real earthquake. So 8 divided by 1.85. So the panel zone has to be roughly 1/4 as strong. And it is widely attributed by the structural engineers in California that the reason this is 1.85 rather than 1.7 favored by Southern California engineers was because Helmut Krawinkler said it should be. Helmut, of course,